Hello and welcome to this first lecture in Chapter 2. In this chapter, we're going to start really getting into some physics and start talking about motion and how to quantify motion in one dimension. What we're going to be studying in this chapter is something called kinematics. And in particular, we're going to be learning about kinematics in one dimension, which is the study of objects that are moving along a single straight line. That can be a horizontal or a vertical direction, and we're going to look at both of those. So what exactly is kinematics then? Kinematics is the mathematical description of motion. We can describe motion using a lot of mathematical tools. We're going to start building those up today. We are going to develop equations that we can use in a variety of different situations for objects that are moving in a straight line. And then we'll look to expand that to objects that are moving in other ways, in a circle, around a curve, or projectile motion. But the basic ideas that we develop here are what we're going to use throughout our entire study of kinematics, which will be our whole first unit in physics. The simplest possible type of motion is motion along a straight line at a constant speed. We call this uniform motion. Now, what this looks like on a motion diagram is dots that are equally spaced apart with equal velocities between each one. So we can see from that we're moving at a constant velocity in the same direction all the time and the same speed all the time. That's the motion we're going to start studying first because it is the absolute simplest that we can. If we were to represent that on a position time graph, it's going to form a straight line. Now it can slope up, it can slope down, and that's going to give you information about which direction the object is actually moving in. For one-dimensional motion, we've already defined that the average velocity is equal to the change in position over the change in time. Now that can be delta x or delta y for change in position, depending on whether we're talking about motion in the horizontal direction or the vertical direction. If we show this on a position time graph, then the position is always plotted on the y-axis and the time on the x-axis, so that the slope of the position time graph is going to tell you the average velocity. If you have a constant velocity, if you have uniform motion, then you're going to have one continuous slope that's the same all the way from the beginning to the end. Now let's look at an example here of a position time graph and see if we can figure out from this graph how the object is moving and what its velocity time graph would look like. So here we clearly have three different parts of the motion. From 0 to 2 seconds, to hit this point, you can see that this object is moving in a negative direction. If you calculate the slope, it's minus 2 meters per second. From 2 to 4 seconds, it's standing still, not moving at all. And then from 4 to 6 seconds, it's moving much more quickly in a positive direction. We calculate the slope there, we get that it's 5 meters per second. So we can tell a lot about how this object is moving just from looking at this graph. What kinds of things could we calculate from this graph? Well, one of the first things that we can calculate is the displacement of the object. Displacement is equal to the change in position of an object. So it's the final position minus the initial position. So if we want to know the displacement all the way from the beginning to the end, it would be the position here at the end, which is 6 meters, minus the position at the beginning, which is 0 meters. So that would be the displacement all the way from 0 to 6. But what if we wanted to find the displacement over some smaller intervals? Let's say that we wanted to find the displacement from 0 to 2 seconds. Well, then our final point would be minus 4, and our initial point would be 0. So we would have a displacement of minus 4 over the first interval. What would it be from 2 to 4? In that case, it would be 0, because we don't go anywhere. We have the same final position as initial position. And if we look at the displacement from 4 to 6, then we see that it's a positive 10, giving us, again, a total displacement all the way from the beginning of 6. We go negative 4, 0, positive 10. We get 6 in the end. The other thing that we can do is we can turn this into a velocity time graph. Now, velocity time graphs are going to be incredibly important. We are going to use these to start solving physics problems. The velocity graph is not going to have the same shape as the position time graph. And that's important to notice. What is shown on the velocity graph is exactly what it sounds like. It is how fast the object is going. And remember that that corresponds to the slope of the position graph. So if we wanted to make the velocity time graph, we again need to know the slope during each of those three different intervals. We already calculated those. In the first interval, the slope on the position time graph was -2. So we have -2 for the velocity. It's a constant velocity because it was a constant slope. During the second interval, we had a velocity of 0. We were standing still. And during the third interval, we had a velocity of 5 meters per second. So we have really these 3 different intervals with 3 different velocities, but they're constant within that interval. So we have 3 different horizontal lines at different parts during the motion. Now finally, let's look at these and assess, make sure that it makes sense. I just want to point out again here that the velocity graph and the position graph look completely different. So the value that you read on the velocity graph equals the slope of the position graph. So if the position graph looks like this, the velocity graph will look like this, right? Always, because that's a constant slope, so you're going to get a constant value on the velocity graph. I'm reiterating this a lot because this is an area where students often make mistakes early on. You want to think that you have a position graph, what's the velocity graph? Often people will try to draw it so that it looks similar, and that's on all cases incorrect. They're not going to look similar. So let's kind of summarize then what we have learned so far about position time graphs. The slope is going to tell you what the velocity is. So therefore, a steeper slope corresponds to a faster speed. It can also tell you the direction. A negative slope corresponds to a negative velocity, and a positive slope is going to correspond to a positive velocity. And I also want to point out here that the slope is a ratio of the interval, so it's the change in the x values divided by the change in the time values. So you can't just simply pick a point on the graph and divide that point divided by the time at that point. It's the slope. It is the change in values, not just the individual coordinates. So let's go back and look at that position time graph and see if we can put some math with this. Our goal here is to develop some equations that we can then use to solve a variety of different types of problems. So consider if you have an object that is in uniform motion along an axis. We're going to call this the s-axis because it could be x or y and the mathematics are going to be the same. So say that it's moving along this line here. This is its position time graph. This is its initial position, this is its final position. How are we going to figure out what an equation is that will allow us to predict where it's going to be at in the future? Well, let's think about the slope-intercept form of a line, that y equals mx plus b. All right. What is m here? M is the slope. Well, what is the slope on a position time graph? It's the velocity. What is x? Well, that's the time, right? What is b? That's the y-intercept. So we can rewrite this equation in this form, where we have final position, that's our y value at the end, is equal to initial position, will be kind of equivalent to the y-intercept, plus the slope times the change in x. This is going to be an important equation that we will use over and over again whenever we have uniform motion to predict where an object is going to be at some future point if you know where it is now and how fast it's moving. So once again, summarizing what we know for uniform motion. For motion with a constant velocity, you can model the object moving as in a straight line at constant speed. You can make a model on a motion diagram, which looks like this with these constant velocities. On a position time graph, it's going to look like a straight line. It can be sloping upward or downward depending on the direction, but it's going to be a constant slope. And the slope is going to be equal to the velocity. So on the velocity graph, if you have uniform motion, it's going to be a horizontal line. Now that can be positive or negative, but it will be always horizontal. Mathematically, the two equations that we have developed so far, our definition of velocity says that velocity is change in position over change in time. We can rearrange this and put it in a slope-intercept form to show that final position equals initial position plus velocity times time. And we always want to think about when we develop a model like this, when can we use this model, when can we not use the model? So this model is only appropriate to use if you have uniform motion. So it will fail if the particle has a significant change in its speed or direction. There are other models that we can use to deal with those situations, but we haven't learned them yet. Finally, I want to finish up by talking a little bit about which of these quantities are vectors and which are scalars. So if you remember, a scalar is something that has only a magnitude, while a vector is a quantity with a magnitude and a direction. We have talked about some different terms here, like distance, displacement, speed, and velocity. Some of these are scalars and some of these are vectors. So distance and displacement first. Distance is a scalar. It does not have a direction. Displacement, however, is a vector, and it's always equal to final position minus the initial position. Displacement and distance may or may not be the same amount. The magnitude of displacement will be equal to the distance only if you have an object that goes in a straight line and doesn't turn around. If it turns around or if it turns and doesn't go in a straight line, then the distance it travels will not be the same as the displacement, because displacement is always just going to be a straight line from beginning point to ending point, irregardless of what happened in between. Speed and velocity are also a little bit different. So an object's speed is a scalar quantity independent of direction. It's just how fast it's going. It doesn't tell you what direction it's moving in. And so in that case, it's always a positive number. Velocity does include a direction. For now, since we're talking about one-dimensional motion, the only directions you have to worry about are whether it's positive or negative. So positive is generally considered to be to the right or up if we're talking about vertical motion. Negative would be to the left or down. That's the only directions we're going to worry about so far. Let's finish with a quick question for you to think about. I'm going to leave this with you to think about, and we'll answer this question at the beginning of our next class period. The ant zigzags back and forth on a picnic table as shown. We want to try to figure out what is its distance traveled and what is its displacement. So remember, distance is you have to track the entire distance that the ant travels. Displacement is simply the difference between its starting point and its ending point. I'll see you tomorrow.